Hello, this is the next video in the video series on the bracket notation for structuring proofs. So in this video we're going to look at a few more examples of how to form sentences using the various symbols that we've introduced in the other video. Let's begin with the following. Suppose I want to say the following into a symbolic mathematical language. Every friend of Tom who is fond of music can play the piano. Okay, so our task now is to turn this into a mathematical formula. The kind of thing that you can put on a single line of a proof that's displayed in bracket notation. We need to introduce a few symbols for that because mathematics doesn't know a few concepts involved in this sentence, like being a friend, or Tom, or being fond of music, or being able to play the piano. In fact, in some sense, mathematics doesn't know about anything. The only thing that mathematics knows about is pure logic. So when you want to express something in this purely logical framework, you do have to give some symbolic interpretation to the basic concepts around which your logical framework is built. And if you want to make use of some information about those concepts that you will need for establishing facts about these using mathematical method, then you would propose axioms that are supposed to capture the basic features of those concepts. In this case, we don't want to prove anything. We just want to write out this sentence in a symbolic form, so we will not need any axioms. But let's see which symbols are we going to need in order to write this formula. Okay, so first of all, maybe the key player here, or at least the only one who's been named by name, is Tom. So perhaps as a first step, we give a symbolic representation of Tom. So let's agree. We're now going to make a table where we describe these representations. So let's agree to write Tom as let me see, because I think in the other video we said that this symbol will be used for truth and the other one will be used for false. So, for true and false respectively. So we don't want to use that symbol unless we type it up and then we put it in a different font. But when I write on the blackboard, it's difficult to achieve that. So, well, actually, why is it difficult? Maybe it's not so difficult. I'm going to use this kind of T for representing Tom. Okay? So that's my symbol that represents Tom. And this symbol is a term because it represents an object. Obviously, you see that the statement here is about human beings, right? There is also piano there and there's also music there, but the main key players here, piano and music are just there to describe properties of certain human beings. So the key players are human beings. So our variables are going to represent human beings. And actually, that's the first thing you want to clarify before you start writing down the formula corresponding to your English sentence. The first thing you want to clarify is, what are your variables going to represent? And so for us, these are human beings, for the reason I just explained now. And as such, we are going to need, so the human beings are the objects in this language. And since Tom is one of them, we're introducing a symbol for it. This symbol is called a term, because a term is what produces objects. Remember, the difference between a term and a formula or a statement is that a term doesn't have true or false value. We cannot talk about Tom being true or Tom being false. That doesn't make sense. Tom is just an object. When we say things about Tom, those things can be true or false, but Tom itself cannot be true or false, right? Literally, in the literal sense. Also, of course, metaphorically, you can think of Tom being true in terms of him being true to his friends or whatever. But that's just an abbreviation. Huh? So Tom is a term, and it takes no input terms, no input variables in it. It's not like x plus y, where we need two objects, x and y, in order to produce the object x plus y. It's not like that. It's more like the number 0, where we are producing an object without any input objects. Okay? So Tom is a term that has no input variables, and we then say that it's a nullary term, where nullary refers to the fact that the number of variables that we need to input to get an object out of this symbol is 0. Okay. Next. Now we want to, I guess the next step is to be able to say that someone is somebody else's friend. We already have a symbol for Tom, and so now we will need a symbol for friendship. So we will need a symbol that will allow us to say X is a friend of Y. And let us use the symbol F for that. And so this is no longer a term, because X being a friend of Y can be either true or false, right? So we are now dealing here with a formula, and so the symbol, when it appears in a formula, will appear in this form. So it will have two input variables. Symbols like these that have input variables and that express a statement are called relational symbols. So F represents a relationship between X and Y. And by the way, those symbols that produce terms, that produce objects, are called functional symbols. And so just to go back to this example with X plus Y, plus here would be a functional symbol, and X plus Y would be a term. Whereas here, F is a relational symbol and XFY is a formula. So XFY is already a formula because it already says something. Okay, we will revise this terminology as we go along. It's not so important for us to know these terms, but eventually it will be useful to quickly refer to these things. So we will be revising this as we progress in the video series. So X is a friend of Y can be represented like this. Now, this is one way of approaching this problem. Another way would be to not to have a separate symbol for Tom, because Tom only appears here once when we want to talk about the friend of Tom, and instead to have a relational symbol that will have only one input variable, and that will express X is a friend of Tom. So we could have instead just a symbol for representing this whole thing. X is a friend of Tom. Because, okay, let's first write this down. So maybe we could write this kind of combining the T and F there, like this, to represent the formula saying X is a friend of Tom. You see, in this statement, the word friend and the word Tom only arise once, right? So they're only used once there. So it might have been meaningful to use this symbol instead. If we had friend and Tom occurring over and over several times in different contexts, not necessarily always together like this, then it would be better to use these separately, because in mathematics we do want to have the number of additional symbols we introduce to be as minimal as possible. And so if we go with this, and we also have a need for these two separately, then rather have them separately and then give up on that one. So we will now actually do both of these versions. Okay? Let's see, what else do we need? Now we need a way of saying that a human being, is fond of music. And again, we have this choice. We could say, we could have music represented by a variable and then a symbol saying that some object is music, or we could just have this whole thing just depend on one single object, the human being that is fond of music. And so in both cases, we'll actually take that approach. X is fond of music. Let's represent it like this, mx. And finally, X plays the piano. Let's represent that like this, px. Okay, so now we are ready to write out a formula that has the same meaning as this English sentence. Now, you see, in this English sentence, there is no X, right? It's like at school when you solve a word problem and you need to figure out what to represent by X so that you can solve for X. Now, in our case, we're not solving for X, but we still need to introduce the X. X is going to be the object that occurs several times in the sentence, and because of that, we need to give a name to it so we can identify two different occurrences to be the same object. And in this sentence, it is the friend that occurs several times, right? We say we have a friend here, some human being who is friend of Tom, and that human being, whichever that is fond of music, can also play the piano. So you see, it's 3 times that we encounter X, but it's hidden, of course. And the first time, it could have all different values, right? It could be all sorts of different friends of Tom, but then each of these friends, those who are fond of music, we should say about them specifically that they play the piano. Okay, so because that human being that's supposed to be a friend of Tom, at least when that human being is a friend of Tom, that person, if that person likes music, that person should be able to play the piano, right? Because we have arbitrariness of this human being, so the only restriction is that this human being is a friend of Tom, but Tom can have several friends, right? So we're not actually even saying that Tom has a friend. We're saying if Tom has a friend, basically, right? So this is how we can see that what we'll be dealing with here will be a universal quantifier. So every X, and now we want to say Remember, at this point, X represents a human being. So what we want is to put a restriction on X first, namely that X must be friend of Tom. We actually also want a second restriction, namely that X is fond of music. And after that, we should claim that X can play the piano. You see, the first two times we're not claiming that X is a friend of Tom, because X is a random human being, right? We're not saying a random human being is a friend of Tom. That's not what we want to say. We want to say, if you take a random human being, if that person is a friend of Tom, and if that person is fond of music, then that person can play the piano. So you see the difference between the assumption that we're putting on X and the conclusion we should be able to derive from that assumption. And so when there is this passage from an assumption to a conclusion, that's an indication of the presence of the implication, right? So some requirement on X should imply another property of X. Okay, now we are almost done. What is the requirement on X? X must be a friend of Tom. X is a friend of Tom, and we have a symbol for Tom. And at the same time, X must be fond of music. And if that is true, then X must be able to play the piano. So let's get rid of unnecessary brackets here. Since this formula reads as one thing, we don't really need these brackets. Right? Okay. The rest of the brackets we do need. Now this bit here, you see, the t there wasn't quantified. The X there is quantified, but not the t. Why? Because t represents a fixed human being. T is not a variable. T is a functional symbol. It represents some specific human being. We're not talking about here every Tom or there existing a Tom. There is some specific Tom we have in mind about whom we're talking. Okay? So in that sense, t is not a variable. It's a constant, like the number 0. And as we said, we don't really need Tom for the rest of the sentence, so we could also write this in the other way, where the difference will be very, very small. So we will just replace that xft with just this other kind of fx, and that's it. Okay. Now, let's do something interesting. Let us forget about this part and let us also forget about this part. And let's replace Tom here with something else, and I'll show you now with what. In fact, I'm going to replace this whole thing with something else. There is a human being whose every friend who is fond of music can play the piano. You see, before, Tom was that human being. Before we were saying that Tom is a human being such that every friend of Tom that is fond of music can also play the piano. But now, we've done something slightly different. We now are saying that such a human being exists. Of course, when we know that Tom is indeed such a human being, then we know that the statement that such a human being exists is true, but we don't care about the truth or falsity of this statement. We just want to translate this into the symbolic language at this point. If I take this formula I got here and replace the t, the constant t, with y, what will I be saying? Then I will be saying here that every friend of y that is fond of music can play the piano. So this whole thing will be expressing some property of a human being y. And so you see, now there is a big difference between how x and how y appear in this formula. X, outside this formula, has no meaning. The variable is bound by the quantifier. So when a variable appears as a subscript of the quantifier, we say that the variable is bound by the quantifier. And this quantifier has a scope until the end of the formula. So if we step out of this formula, right, we don't know what is x. There is no x actually. But there is a y. So what do I mean when I say there is no x? X was just a name we introduced when we wanted to express some property of y. And once we express the property, we can forget about that name. And we have to forget about that name. We can't refer to x afterwards by the standard conventions of mathematics. But y is in a different role. We don't want to forget about y. This statement, this orange thing, is a property of y. And maybe if we pick y to be Jane, that thing maybe will be false. If we pick y to be Luke, maybe that property will still be false. If we pick y to be Tom, then maybe that property will be true. And so the variable y, which is, when it is not quantified, we call it a free variable, is a placeholder for anything we like. And we can substitute things into y. We can't substitute anything into x because of the quantifier business. X has some specific designation which does not make it available for substitution. But y can be substituted into. So this is kind of saying y is red, if you like, or y is blue. No, it's not about blue or red. It's about every friend like in music should play the piano. That's what the property says. That's a property of y, and we could now consider this property for different values of y and judge whether for those values of y that property holds or not. And what we want here in this sentence now, the modified sentence that we created here, what we want there is there to exist such a human being y, the one that has that property. So to get that sentence, all we need to do is to add in front of this the quantifier that exists with the y. And these brackets that can be added are also, in this situation, can be also removed because it's obvious where the placement of this bracket should be. So now we got the sentence, this formula. So by the way, in mathematics, a sentence is a special type of formula where there are no free variables that are present inside the formula. So this thing with the exists y in front would be called a sentence, but without that exists y, that was a formula, which is not a sentence. Otherwise, every sentence is still a formula. Okay, so now we've got something that expresses that there is a human being whose every friend who is fond of music can play the piano. Right? If we read it from left to right, we see that exists a human being y. Remember, variables represent a human being, so that's why we can say human being every time we read out a variable. That exists a human being y such that every human being what? Every human being what? Some implications should hold. And how do we read this? If the left-hand side, then the right-hand side, right? Such that every human being that is a friend of Y and is fond of music, in other words, every human being, for every human being, if the human being is friend of Y and is fond of music, then the human being plays the piano. So every human being that is friend of Y and is fond of music plays the piano. You see how we transition in English from if-then construct to that construct. Every X that has the property of being a friend of Y and liking music plays the piano. In other words, for every X it is true that if X is a friend of Y and X likes music, then X plays the piano. Okay, so this example that we discussed today, well, why today? Maybe we will discuss other things as well today. So I shouldn't be saying today. I should rather say in this video, right? So the example we discussed in this video, it gave us the opportunity of paying attention to a few different aspects of designing formulas out of English sentences, right? For example, this whole idea of free and bound variable emerged there. Also, kind of the main thing is when you're putting a condition on your object, like we had a condition on X before we could say that X must play the piano, how to deal with a situation like that when it forces us to introduce implication. And also how we could transition between talking about a fixed object like Tom, for which then we will have a constant, to having a variable for it like Y, and then expanding the sentence with some prior information about Y. Like the statement we have now that says that there is such a human being Y that has the property that every friend of Y that likes music can play the piano. Okay, so that's the end of this video. Of course, the techniques we discuss in this video are not supposed to be only just for this specific example. You can see how these things can generalize, and maybe you can also see the whole spirit of how these things are done and be able to create formulas out of English sentences which do not necessarily look like this one, but still kind of figuring out the methodology behind the whole thing. So just a summary is, a very, very general comment is that English sentences can have logical meaning, right? Mathematical sentences also have logical meaning. And the process of translating from one to the other is a process where we retain the logical meaning as close as possible to the original one, right? But of course, we will never be able to check for sure that the translation is valid because the English sentence is not a mathematical construct. We can only check things in a mathematical language. That's the only language that allows us to be sure about computation. And if you want to check that something is correct mathematically, first we need to translate it into the mathematical language. So we can never really check correctness of the translation because the original thing is not part of mathematical language. But once we establish such translations, then we can use the mathematical language to check various things like equivalence of a statement like this in English and another statement in English, which by not using mathematics we might not have seen immediately that these two things are logically equivalent. And so keep in mind that this is how mathematics works. That's very relevant for those of you who are interested in applications of mathematics outside mathematics. Whatever life phenomena mathematics applies to, we always need to first translate into the mathematical language, and then something might be lost in that translation. And so we use then experiments and statistical data perhaps to confirm that our translation is valid, right? At least, as I say, we cannot prove, but we can at least be certain up to certain probability, because of statistical investigation that we did, that our what is called, I mean, such a mathematical environment obtained by such translation is usually called a mathematical model, right? So we use statistics and various other things to be certain as far as possible that the mathematical model faithfully describes the real life scenario. But of course, 100% certainty is not possible there. Just the kind of certainty that is possible for mathematical theorems, for proving mathematical theorems. And this is why, I mean, even in the proof of mathematical theorems, we always kind of still rely on our common sense, right? Or if it's a computer that checks the proof, we rely on the computer's common sense, right? So there is no perfect precision. We strive towards perfect precision, and mathematics is what we encounter on this journey. And after some point on, it's always mathematics. But even mathematics does not reach perfect precision, right? Because we're still human beings who, I mean, if mathematics was a perfectly precise mechanism, maybe it is, by the way, but it would be difficult for us to confirm that because we are a mixture of mathematical and non-mathematical entity, right? Not to go too much into philosophy, I wanted to say just that so this step of transitioning from the real life scenario to the mathematical one, and never being certain if this transition is completely accurate or not, this is one of the reasons why pure mathematicians are not particularly interested in applications, because then it puts us into, I mean, I'm a pure mathematician, and so I am interested in life in general, including applications and all sorts of things, but when I'm interested in mathematics, for me, that interest has nothing to do with the applications, because the reason why I like mathematics is because of its precision and because of its internal beauty, and the fact that mathematics is applicable to real life, for me, is kind of a bonus and maybe deep down some motivation, but the actual process of application is not what I'm interested in mathematically speaking, in terms of my mathematical interest. So this this lack of precision in the modeling of mathematics and applications of mathematics is what pure mathematicians kind of makes resistant to look into applications. But at the same time, I think it is what makes applied mathematicians and other scientists love what they do, because I think that there is some beauty in uncertainty, and in kind of trying to figure something out which you will never know for certain, but you can make further and further progress towards certainty. I think there is some beauty in that, and I can imagine that if one type of people are kind of put off by that feature of the interaction between mathematics and the rest of the world, and the other type of people are attracted to the rest of the world exactly because of that feature. Okay, so I mean, this discussion is not about kind of subjective opinions and tastes of different people. What we're trying to do here is to describe the reality, how it works, right? And so nobody's saying that mathematics is superior to everything else because it has this precision. Just like nobody's saying that music is superior to everything else because it can affect your emotions in a way that maybe something else cannot, right? So it's not about superiority that we're talking about here. It's about each individual discipline that has emerged as part of human activity having its own beauties and its own merits. And it's important to understand the scope and the limitations of these, and also the richness of these merits, in order to understand completely objectively and faithfully how the universe works. Okay, great. That's it for this video.